So this lecture will learn about the basics of SPICE, which you will use for all your assignments. SPICE is a class of circuit simulators that are used to simulate electronic and electric circuits. There are actually today many different versions of SPICE which have been developed by different companies, mostly for their own use, and they have different facilities and different capacities. The original SPICE was developed at the University of California in Berkeley. I think the first version came out in 1972. Now, of course, there are many other circuit simulators also, but SPICE remains the most widely used circuit simulator. We, for our course and for the assignments, will use a version called LTspice, which was developed by Linear Technology. Linear technology is of course now taken over by analog devices. So you can download LTspice from this link here, which you should because you need it for your simulations. Okay. SPICE, this is just background information which you really don't need to know at all, but just general knowledge. Is that SPICE for simulating circuits, it uses what is called as modified nodal analysis. So it's a modified version of nodal analysis in which the simulation and the method finds the currents in the independent voltage sources also, along with all the nodal voltages. For nonlinear circuits, SPICE uses the Newton-Raphson method. And so of course you'll encounter non-linearities as soon as you have electronic circuit elements, diodes, bipolar transistors, MOSFETs, etc. For transient analysis, SPICE uses either gear or trapezoidal or modified trapezoidal integration. This is just general knowledge. You can forget as soon as you heard all this. As I have mentioned before, there are many models of MOSFETs that have been developed in the last 50-60 years. The one we kind of derived, the simplest model. Okay, so in SPICE, different MOSFET models are defined or identified by a level. So the level number. So level 1 represents or refers to the simplest model we have derived in lecture 3. I had talked about the BSIM 3 model, which we will use for all our simulations and designs. That is level 49 in the version of SPICE in LTspice that we are using. So there are many models, and each version of SPICE will have a different set of MOSFET models available to it. And so for example, many companies, they have their own proprietary MOSFET model which they use in the circuit simulator, because the MOSFET model is one of the most important and critical things in designing chips, all chips in the world. So it is a very important and therefore often confidential model. All right. SPICE can do many different analyses. Here are the 4 that you will use significantly. So one is, and that I'll come to the dot later in case you are not in, so maybe you are familiar with SPICE, in which case all this is a revision, but that's okay. So OP is a DC operating point analysis. So you define a circuit, specify it to SPICE, and it will just simulate it once, and it will tell you what all the DC currents and voltages are in the circuit. A DC is an analysis in which you vary a certain current or a voltage source value over a range, let's say some gate voltage from 0 to 5 volts over steps, and then you tell SPICE to do a DC analysis. So it will do an analysis for many different values of that independent voltage source. .tran is a transient circuit analysis, so SPICE will simulate the circuit as a function of time. .ac is the AC or the small signal analysis. It is basically an analysis as a function of frequency, and therefore it is basically a Bode analysis. The output are magnitude and phase Bode plots. One thing to remember about this analysis is that this is a small signal analysis. That means all transistors, diodes are replaced by their small signal models. We'll discuss small signal models after maybe 4 or 5 lectures. Okay, SPICE also does other analyses which you will not use. One is called a Fourier analysis, which finds the frequency components of any signal. Dot step, which steps a circuit parameter. So the dot DC, you can vary the value of a current or a voltage source in the circuit. Dot step allows you to vary any parameter. So you can vary the resistance value, capacitance value, and simulate for a range of values of circuit parameters. Dot temp does a temperature sweep. So you can vary the temperature over a range. All right. The first thing, of course, that one needs to do while starting to use a circuit simulator is that one has to describe the circuit to the simulator. The circuit we want to simulate, we have to describe it to the simulator. Now, there are two ways that one can describe the circuit. One is in a text form, and so one writes what is called as a net list in a text form. For the first 3 SPICE assignments, you will use netlists. All right. That is one way. The other is to do what is called as a schematic description, which is basically in terms of symbols for all the circuit elements, and you kind of put them together. We'll look at this perhaps later. For the 4th assignment, you can either use a netlist or a schematic. I'm leaving it to you. I'm specifically asking you to use netlists for the first 3 assignments because most students tend to start off by using schematics and never get around to learning how to use netlists. And schematics are actually overall a better way of using or describing circuits, especially as circuits gets larger. But for small circuits, netlists are far more convenient. And many of our circuits, so in the first 3 assignments, the circuits will be very small, extremely small, and the netlist is better. So I would like you to learn to use netlist so that this stays with you later in life also. Alright, so let us learn how to write a netlist, which is how to describe a circuit to SPICE in a text form. So these are the steps one must follow while writing a netlist or before writing a netlist. So first we of course must draw this. When we are going to use SPICE, we're going to simulate some circuit. So here is a representative circuit that I'm using as an example. So the first thing you do is, of course, you draw the circuit neatly on paper. Step 1. Step 2, give each node a name, right? And the name can be anything. It could be a number 1, 2, 3, 4, 5, or here the nodes are named as G, D, S, and DD. They can be anything. It's up to you to name them whatever you want. And of course, there is a ground node. So you define a ground node. And then name each circuit element. So each circuit element must have a unique name because we are going to describe the circuit in terms of these unique element names to SPICE. Now there is a certain convention to be followed while writing these names. So let's look at the convention. So while describing a circuit element, the circuit element names must begin with the following letters. So if I have a voltage source, an independent voltage source in the circuit, the name must begin with a V. So for example, here this is VG, VDD. After V, it can be anything you want. Resistors must start with an R. MOSFETs must start with an M. Alright, and so on. I for independent current sources, resistor, capacitor, inductor, bipolar transistor is Q. I really never have figured out why It was not called a T or a B, but anyway, that is convention. And these are the four controlled or dependent sources. So voltage controlled current source. Oops, I'm sorry. This is voltage controlled voltage source. This is voltage controlled voltage source. Okay. So voltage controlled current source, current controlled current source, and current controlled voltage source. All right, and the specific formats of how to specify are you can find. I'm not describing this in detail here because all this is there in the help file that is available with the simulator. I'll show you the help file by the end of this lecture. D for diode, X for sub-circuit. So a sub-circuit is like a subroutine in a computer program. So you can describe a sub-circuit, then use it multiple times in the original circuit. All right. So this is a circuit, and I have of course named all the nodes and the circuit elements. Now let us write the netlist given having drawn the circuit. So when you write the netlist, the first line is always a comment line. The SPICE will not read the first line. If you want to insert a comment line other than the first line, you put a star in to begin the line, and then you describe the circuit. So this is a description of all the circuit elements, and there is a certain format. So you take each circuit element, so let's say VDD, and you write the circuit element name, and then you write the nodes between which it is connected. So VDD is connected between the node DD and ground. So ground is always 0, or 0 represents ground in SPICE. G and D also represents ground. So you can use either 0 or G and D, it is your preference. So for a voltage source, the format is the name of the element, positive terminal, negative terminal, value of the voltage source. So this value I have given as 3 volts. I have given values here, which should be there, of course. I mean, each element has to have a value, which I forgot to mention. RD connected between DD and D, and it has a value of 2 kilo ohms. RS is connected between S and 0, 1 kilo ohm. VG is connected from G to ground, and I have a format here. I'll come back to the format just in a minute. DC value, AC value. MOSFET, drain, gate, source, body. That is the order in which the terminals must be specified. A MOSFET has 4 terminals. So drain, gate, source, body. I have not shown the body here. So the body has to be, there is a body, and in this circuit the body is connected to ground. Then there is a name here, a model name, and then there is the length of the MOSFET and the width of the MOSFET, which must be specified. So I'll come to these. So let's discuss these one by one. Okay, so there is a suffix here K, there is a suffix N, suffix U. So this is, let's look at suffixes that SPICE recognizes. So these are the suffixes. T for tera, 10 raised to 12, G for giga, MEG for mega, K for kilo, M for milli, U for micro, N for nano, P for pico, F for femto, 10 raised to minus 15, A for atto, 10 raised to minus 18. So I'm assuming pico to giga you are familiar with. Maybe T, F and A are new to you, so please get familiar with these. A lot of MOSFET capacitances are in femtofarads, as we have seen already. Also, this mega, MEG and M, one has to be very, very careful, because M is milli, often mega. I have done this many times. I want to specify resistance in mega ohms, and I'll write 10M, and it will become a milli, and of course the simulation results will all come out wrong. Alright, voltage and current sources, as I said, the convention is name, positive terminal, negative terminal, DC value, AC1. So one voltage source here in SPICE can represent a sum of DC and AC voltages. Alright, so when we specify this 0.9 AC1, then actually SPICE treats this statement as Vg equal to 0.9 volts plus 1, that is this one, cos omega t volts. I'll come to the omega in a little bit. So this is what Vg is treated as. Now if I do a DC analysis in SPICE, or if I tell SPICE to do a DC analysis, it will take only the DC value. If I do an AC analysis, it will take the DC plus AC value. Alright. There are other things. The voltage source can be a DC, can be AC, or it can be other things. It can be a time dependent voltage source. So it can be a sinusoidal with this format. So you specify a DC offset, the amplitude of frequency. It can be a pulse, and this is the format. I'm not describing this right now. You can read it up. It can be a piecewise linear function of time. It can be an exponential function of time, or it can be an input file called a dot wave file. Alright. So these are the possible types of voltage sources, and current sources, same thing. Independent sources can be any of these types. MOSFETs. So as I said, there are 4 terminals. So one specifies the 4 terminals. Then one puts what is called as a model name, and then the length and the width. So this is the format. Now let me talk a little about MOSFETs. So when a chip is fabricated, there will be millions and billions of MOSFETs on the chip. And the chip will have all MOSFETs with the same fabrication process, and therefore all the MOSFET parameters such as threshold voltage, lambda, mobility, oxide thickness, all of these will be the same for all MOSFETs on the chip. Well, all N MOSFETs will have the same, all P MOSFETs will have a different set of values. The length and the width of the MOSFET can be different for each MOSFET. Alright, so I have a million MOSFETs. Each MOSFET will have its own width and length. But the rest of the parameters are all the same for all the MOSFETs. Therefore, while specifying MOSFETs to SPICE, one needs to specify the model parameters, all these VT and Reox and lambda and all that, only once, because they are the same for all the MOSFETs. So that's why one defines a model, and I'll come to the model specification in a bit, and one specifies the length and width of the MOSFET on the MOSFET line itself. So if I have 5 MOSFETs, I'll have M1, M2, M3, M4, M5. The model name will be the same. The length and width will be different for each of these 5 MOSFETs. Alright, so L and W must be specified for each MOSFET separately, but the model will be specified only once. There are actually other parameters that need to be specified here also. We'll come to that when we discuss the second assignment after a month or so. So today in this lecture, I don't want to overwhelm you with too much information. One more thing I must tell you is that although I said that all the MOSFETs on a chip have the same parameters, actually that's not absolutely correct. There are in a very large chip, a VLSI chip or an SoC, there are about 4 or 5 different types of MOSFETs. Alright, so a million MOSFETs may be one type, another 50 MOSFETs may be another type, and another 5 million MOSFETs can be a third type, like that. But a large number of MOSFETs are of the same type, and so their model parameters will remain the same. Alright, so what we did here is where was that? I'm sorry, I'm going back. So this is the circuit description. So this is the netlist for the circuit. So there are 5 circuit elements, and we describe them in 5 lines. So that is the first thing we do when talking to the circuit simulator. We describe the circuit. There are other things we must do. we must tell SPICE what we want to do. We want it to do with this circuit. Also, we want to specify this model that which is not a circuit element, but we must tell SPICE what the model parameters are. So in the netlist, anything that begins with a dot is called a dot command, and that indicates to SPICE that this is not a circuit description, it is something else. So circuit description will begin with a letter V, R, I, Q, M, etc., etc. If it begins with a dot, SPICE knows that okay, something else is being informed to the simulator. So for example, the dot model statement describes the model parameters. So we say, because we have a MOSFET and we say the name of this model of the MOSFET is N model, we must tell SPICE what this N model is. So the first thing we tell SPICE is, well, this is an NMOS model. So we say N model is an NMOS model, and then we specify all the parameters corresponding to the NMOS that we want SPICE to use while simulating the circuit. So for us, these will be the BSIM3 parameters, and I'll show you the list. Okay, so that is one type of dot statement. The other type of dot statement is tell SPICE what analysis we want it to do. So as I just said a few minutes ago, it can be dot DC, dot AC, dot OP, dot transient, etc., etc. So let's say for this circuit, we want SPICE to simulate this circuit for the gate voltage varying from 0 volts to 2 volts in steps of 0.01 volts. All right. So the DC analysis statement has this format. So you say do a DC analysis, vary this voltage source or current source. So we are telling it to vary VG from some value to some value and the increment. All right. So it will do a DC analysis at 0 volts, 0.01 volts, 0.02 volts, all the way up to 2 volts. So it will do 200 analyses by this one statement. Okay. So dot OP is the other. So for example here, no, okay, it's okay. Dot OP, as I said before, it just do one point analysis. Dot AC, I'll describe this briefly. Is as I said, this is a small signal Bode plot, and the format is you tell SPICE to and so as I said, this is a frequency analysis. So we are telling SPICE to vary the frequency from 10 Hertz to 1 gigahertz. So that are these two numbers, and we are asking SPICE to vary the frequency logarithmically, which is the DEC, which is decade, and we are telling SPICE simulate it for 50 points per decade. So in the decade from 10 Hertz to 100 Hertz, SPICE will simulate the circuit 50 times, then 100 to 1000 50 times, 1000 to 10,000 up to 1 giga. All right. Instead of DEC, one could use LIN, which is a linear variation, and that is used when the frequency range is much smaller. Typically for our purposes, when one is trying to simulate resonance circuits. And the transient analysis, usually one just specifies for how long we want it to simulate. So 5 milliseconds is an example here. All right. Okay, so this is a final netlist. So it has a circuit description. We are telling SPICE to do a DC analysis, and we are specifying the model. This is of course incomplete because, as you will see, this list is very big, so I have not included it here. So this with that we can simulate this circuit. Okay, so I'm sorry, I'm not going to the next lecture yet. So I'm going to show you how to use very quickly the SPICE. So I'm going to demonstrate the use of LTspice now. So I clicked on this icon, which gives me an LTspice window. So let me close this one. And we'll open a file. So by the way, I have put a file called 180 nanometer BSIM 3 parameters 2020 in the notes folder of LMS. So you can take it from there, download it from there and use it, because these are the BC. So let me open this first. Okay, I can open it like this, I think. Yeah. Okay. So these are, so this is dot model, and MOS, as I said. And by the way, so the plus sign indicates to SPICE that this is a continuation of the previous line. So these are the BSIM3 NMOS parameters that you are going to use. All right, and then below it is a list of PMOS parameters. All right, so as I said, this list, so I got this from here a long time ago. I don't even know if it is there anymore. In any case, I have modified it slightly also. So there are, if you count this number, there are more than 120 parameters in this BSIM model. All right. So okay. So what we did is I have the parameters. Now let me copy paste the netlist onto here. All right, so this is my netlist. Now this is my complete netlist, and I can run it to do a DC analysis of this circuit with VG varying from 0 to 2 volts. There's an icon here, run. So I run it. When I run it, it opens a plot window. As whenever there is analysis, not .op, any other analysis, it will open a window, and on the x-axis it will show the variable that we had varied. So VG was varying from 0 to 2 volts, and then we can go to this icon for graph, and we can plot many different things. Let me open this. I hope you are able to see this. So you can plot all the voltages in the circuit, all the currents in the circuit, and you can also plot all the currents of the MOSFET. All right, so let us plot the voltage. So this format is V at node D. All right, so in fact I want to plot V at node D, which is in some sense the output voltage. And so this shows us how the output voltage or the drain voltage varies as a function of gate voltage, as a gate voltage varies from 0 to 2 volts. In fact, you can spend a couple of minutes later on to understand why the voltage is behaving like this as the gate voltage increases. All right. Now LTspice can do some things with these voltages. So if I hover the cursor on top and I right click, it opens a window in which this VD is written, and I can write any algebraic expression here, and it will plot that algebraic expression. So for example, if I multiply this by 5, so the current here, voltage here is 1.623 volts. So if I multiply this by 5, then that voltage gets multiplied by 5. So it is plotting this quantity. So any algebraic expression it can plot. One more very important and nice thing it does, it can plot the derivative. So I'm going to plot the derivative of VD. And actually it is the slope of VD, and the symbol is D. So D of VD will plot the derivative or the slope. So I plotted minus because I wanted a plus quantity. So this is a plot of dVD, dVG. All right. So the y dy dx basically. All right. So you can do derivatives also. In fact, you will use this in the first SPICE assignment and subsequently also. All right. So this is a very quick introduction to LTspice. The rest I think you will figure out yourself. It is very easy to use. Okay. All right. So that is the end of this lecture. Next lecture we'll talk about assignment 1 and MOSFET parameter extraction with SPICE.